Işık nerede? Onu önce bir deneyeyim. Heh, tamam. Okay. Hello. So can you hear me? Yeah, I guess yes. Okay, the title of my talk today is Magic Square Game in Spin Systems with Dzyaloshinskii Moriya interaction. Due to its difficulty in pronunciation, I will usually say DM interaction throughout this talk. So let me first introduce our research team. Azmi Altuntaş from Okan University is the guy who I have been working for several years. Volkan was our joint PhD student. Now he's working at Okan University as well. And Cihan is an interesting guy. Well, my background is in computer engineering, and I became more interested in quantum computation and quantum technologies and optics. And Cihan is actually a civil engineer. He was first interested in the ocean waves and then became interested in optical waves. That's how we met each other and started to work together in optical rock waves and Zeno paradoxes, etc. And these two are my former students. Still, we are working together. They are PhD students in NUS and University of Tokyo, and these are my collaborators. And this interaction is some anti-symmetric exchange interaction. It's a contribution to the total magnetic exchange interaction between two neighboring magnetic spins. So it was postulated in like almost 50 years ago and identified as some spin-orbit coupling. Due to spin-orbit coupling, this interaction takes place. So it is interested in a variety of branches of science, from spin Hall effect switching to some sky meryons and some other metal films, for example. And it's a hot topic still in a lot of fields. And there are efforts for measuring it, also for explaining its physics. So since it is a neighboring spin interaction, I was interested in it from the perspective of quantum information, because to me it can create some entanglement, or at least excite some entanglement, which in Turkish I prefer to use the word dolanıklık instead of dolaşıklık. It was first studied in 2007 for a simple spin chain, and it was shown that at some fixed temperature, the thermal state, the thermal entanglement of this spin chain, actually this is only for two spins, it is excited by the strength of this interaction, especially in this ferromagnetic part. So actually this photo was the one, this figure was the one made me interested in it when I first saw in Professor Müstecaplıoğlu's paper. I liked the colors and became interested, oh, what is it? And I started to study it. So in the X, it writes X here. In the horizontal axis, T. In the horizontal axis, there is the temperature, and the vertical axis is for the strength of this interaction. So as the temperature increases, entanglement of the particles between the particles is decreased as expected. But if there is this interaction at an increasing strength, then it excites the entanglement, and the entanglement of these two particles may even reach the final, the maximum level. So this is one example studied for how this interaction excites the entanglement between quantum particles. Since then, since this 2008, 7 and 8 papers, this interaction was studied extensively for qubit-qubit systems, qubit-qutrid, qutrid-qutrid, etc., for a wide range of spin models, also under magnetic fields. People always studied the entanglement in terms of the entanglement measures such as negativity concurrence and the violation of Bell inequality. And the general result is that, so thermalization always destroys entanglement, and magnetic fields usually decreases the entanglement. There are some counter examples though. And DMI, I think always, as far as I studied, always increases this entanglement. Therefore, if we are doing some quantum information task with spin systems, then it's better to choose some materials having this interaction between its spins. So, for entanglement, DMI was studied and understood, and I thought, okay, what about something else? In this cartoon, like the guy is wondering if there's an alien, some alien comes and he says, oh, okay, you exist, now I wonder if there's another alien existing. So I said, okay, for entanglement it works, but what about quantum metrology? I'm not going to detail quantum metrology here, but it's about how precise we can make some measurements. And for the quantification, we usually use quantum Fisher information, or QFI shortly. And QFI quantifies the metrologic capability. Roughly, we can state like that. And we maximize it over the directions X, Y, Z, and choose the maximum in the direction which is the maximum. So the interesting thing about quantum metrology is that if we have n particles, if these particles are separable, the best state of these separable particles, the QFI of these states scale with the number of particles. Therefore, total quantum Fisher information per particle is always 1 for separable states. However, if we have entanglement between these quantum particles, then the best states scale with the square of the number of particles. Therefore, QFI per particle can achieve n. So this is a great advancement in quantum metrology. And the limit which is provided by the best entangled state is called the Heisenberg limit. And any state which surpasses this limit of so this limit is called shot noise limit for the best separable states. Any quantum state that exceeds this value, 1 is called useful, in a sense that it's useful for sub-shot noise limit metrology. But the point is that this quantum Fisher information is not an entanglement monotone. It's not like an entanglement measure. So it can decrease or increase with local operations and classical communications. States which are identical under local operations and classical communication may provide different values of quantum Fisher information. The most interesting example is that among 4 Bell states, 3 of them achieves the maximum value, the 2 QFI equals to 2, but the last one, 0, 1, minus 1, 0, provides 0 quantum information. But if we apply some LOCC operation, then we can increase this QFI of this state from 0 to maximum level. And so if the state was the best state here, and if it is in the pure state, if there's no decoherence on the state, it provides the maximum quantum Fisher information. However, if there is decoherence, of course the metrological capability decreases, but since it's not a monotonic measure, you see here as the decoherence strength of the amplitude damping channel increases, the quantum Fisher information first decreases, and then it tends to increase back. Here, so it's obvious that the entanglement during this interval from 0 to 1, entanglement always decreases, but QFI may stay constant or even increase. That's because it's not monotone. And we first wanted to find the relation between quantum Fisher information and quantum entanglement measures. Because most of the measures like this negativity and concurrence are valid for bipartite states, no matter how many particles they are consisting of by but bipartite. However, this quantum Fisher information is about multipartite entanglement, and there is a quest for finding a general entanglement measure, a multipartite entanglement measure based on quantum Fisher information. For this, we had proposed an optimization method, an LOCC optimization method, in order to find the maximum potential quantum Fisher information of a quantum system. And well, there are some relations between the entanglement measures, some behaviors, some dependencies between negativity and concurrence, or relative entropy of entanglement, for example. Here, we found the same relation between relative entropy of entanglement and quantum Fisher information optimized in our method. So this curve, the red ones, obey the same relation rules between the entanglement measures. So we asked whether this DM interaction can excite quantum Fisher information. Okay, we know that it excites entanglement. It always excites entanglement. But since this DM interaction is not an entanglement measure, and it is related but not directly proportional to entanglement, this question was very interesting for us, whether it can really increase the quantum Fisher information for some particle. And we showed that yes, it actually excites. In some cases it excites, and in some cases there are at least some regions that it excites and then decreases and excites. So the ferromagnetics spin chains become even useful, which means that they surpass the quantum Fisher information of the separable states. So this was about the quantum metrology, the effect of DM interaction, the positive, the constructive effect of DM interaction in quantum metrology. And we said, okay, entanglement was okay, and we showed that quantum metrology is okay. What else? Okay, why don't we play a game? I'm interested in game theory. Well, my motivation in game theory is actually twofold. First is this. Quantum mechanical resources introduces two types of advantages. One is that if we have quantum mechanical resources, some tasks, such as factoring numbers or search in some unsorted database, becomes faster. Just some increase of performance in a task that any classical device can perform. But the second type of advantage of quantum mechanical resources over classical resources is that they can perform some tasks which are impossible to realize with classical resources, such as quantum teleportation or superdense coding or sharing private keys. So this was my first motivation, to find some tasks that quantum mechanical resources perform better than classical resources. And the second reason of my motivation is that most of the quantum tasks are basic, like quantum teleportation. So as soon as we know the type of the entanglement we have in our hand, for example, among the four Bell states, if we know which one we have, then everything is so simple. If this state is maximally entangled, like it's a pure state, there's no decoherence on it, then we know the performance of the task. The higher the entanglement is, the better teleportation you can do. And the lower the entanglement amount is, the worse your performance is. But if we have more sophisticated information processing tasks, then would the amount of entanglement be sufficient to characterize the performance of this task? This was my question, and that's why I was interested in game theory, because things got more sophisticated there. Okay, so let me first introduce magic square. Magic square is a 3x3 matrix and filled with binary entries. the rule here in the magic square that the sum of the entries in each row shall be even number, so either 0 or 2, and the sum of the entries in each column should be an odd number. So if we try to fill this matrix with binary entries, we see that we can fill only 8 of these 9 cells. So one of these cells is inconsistent. So we cannot have such a magic square. Normally we cannot have. Okay. A game can be played using this magic square. So in this game, Alice and Bob are one party and they play against the referee. So before starting the game, Alice and Bob are free to determine any strategy and share any type of resources. Okay, in this part, they are limited to classical resources. And once the game starts, they are separated and they cannot communicate or share with each other, just like the prisoner's dilemma example. And when game starts, referee says one number, the number of the row for Alice to fill, and one number, the referee says one number, the number of column to Bob, so that they fill one column and one row, so that the total of the entries of the row shall be even number, and the total number of the entries of the column is an odd number, and the intersection bit is the same, so there is no problem. For example, referee says first row to Alice and first column to Bob, or second row to Alice and third column to Bob. So from this square, we know that Alice and Bob can win the game only in 8 cases among 9 possible cases, because there is one cell, one instant among 9 that they cannot win. Therefore, it's obvious to see that the maximum winning probability with classical resources is only 8/9, so less than unity. Okay. So what if we have quantum resources and have some quantum mechanical toolbox? Can we achieve a unit probability of winning? This is the question in Magic Square game. It was found that if Alice and Bob shares a 4-qubit state before the game starts, they can share anything. So instead of classical resources, if they are allowed to, if they have quantum mechanical resources, a 4-qubit, 4-particle state, and Alice takes the first 2 qubits and Bob takes the third and the fourth qubits, and they determine a strategy. The strategy is only 3 operations according to which row the referee says to Alice, and 3 operations for Bob. So they predetermine these operations as the strategy of the game to play before the game starts. And when the game starts, referee says the numbers. Alice apply one of the operators among those 3, so does Bob, and they measure their qubits in Z and find 2 classical bits, and it is shown that they can achieve a unit probability of winning. Therefore, this is a very simple and elegant example of how quantum mechanical resources outperform classical resources. And this is a good task for me because it's a little bit more sophisticated than usual teleportation or super dense coding examples. So I wondered whether the DM interaction can increase the winning probability in such a game. For example, if the state in their hand is not pure but it is subject to decoherence, or if this is a terminal state, not a pure but a mixed state, therefore the probability of winning would be decreased, can DM interaction excite or increase this winning probability, just as it does in, for example, teleportation, in usual basic quantum communication tasks, or in quantum metrology. So I designed a simple, which one? This one, okay. A simple spin chain so that it gives this state when the temperature goes to 0. the absolute zero, that spin chain becomes this state, so that the probability of winning is unity in the limit of zero temperature. Okay. So this is a two particle spin. We take two of them and swap to second and third qubits, so that Alice takes the first two, Bob takes the last two. And okay, it's not, of course, very practical that in a spin chain, Alice takes two of them and goes somewhere, Bob takes two of them and goes somewhere, but fundamentally it's important. So here we have DM interaction or magnetic fields, for example, if there's external magnetic fields, inhomogeneous magnetic field. The solid lines represent the results for DM interaction. So for some finite temperature, these colors are for different temperatures. The higher temperature is the lower logarithmic negative one valid measure of entanglement. And external magnetic field decreases the entanglement of this four-particle quantum system as expected. And DM interaction, the strength of DM interaction increases the entanglement, the solid lines, as expected. But when we calculate the probability of winning of the game, no matter temperature, so just like the temperature or external magnetic fields, DM interaction, although it increases the amount of entanglement, it decreases the probability of winning. Therefore, it's revealed that not only the amount of entanglement is something that's sufficient to characterize the performance of our tasks. Because as the tasks become more sophisticated, then we should find some other performance criteria, such as here, Moriya interaction increases the entanglement, which is required for the unit probability or for high probability of winning of the game, but it decreases the probability of winning. Because the total amount, or the physical meaning is that the total amount of entanglement increases, but the structure of entanglement turns to some other state. So the state becomes, the state starts something like this, and when thermalization or external magnetic fields are introduced, the state becomes mixed. DM interaction changes the state in such a way that the entanglement is increased, however, the winning probability is decreased. So this was the final result, the conclusion. Okay. This is our university, Işık University, Şile campus on the coast of Black Sea, where we were a student at that time. And now I'm working here. Okay. Any questions?
The last week you mentioned the interaction increasing the entanglement but still decreasing the probability of winning. Yes. Is it something peculiar to this game, or do you know if it... Well, do you expect it to hold in general? Well, why? I mean, it goes against my intuition.
Yes, this is... Well, at first I thought it would increase the probability of winning, and when I saw that it was against my intuition as well, so I started to study some other games to find a general rule. Now I'm working on that. So this was the first example which is against my intuition. Well, but at first I didn't think that deep. I just wanted to find some quantum task apart from teleportation, metrology, etc., some sophisticated quantum task that DM interaction really is good for. But it turned out to be opposite. So it became more interesting for me. And now I'm I'm working on some other quantum games, and I'm learning more, I'm like deeper the theories of quantum games so that I can find a general rule for this.
Thank you.
Any other questions? If not, let's thank the speaker again. Now we have short talks, and our first speaker is Professor Bilal Tanatar from Bilkent.